Alright, so we're going to talk about similar triangles and indirect measurement in this lesson. And moving on to this vocabulary section here. Indirect measurement allows you to use properties of similar polygons, so today that's often going to be triangles, to find distances or lengths that are difficult to measure directly. So if you look at the example here, we have a person. That person stands 5 1/4 feet tall, and then we also have the shadow, and you're going to see this a lot in the examples today, that it's often the height of something and then the shadow. So the shadow that's cast from the person is 6 foot in length, and then we also know that there is a light pole that casts a shadow that is 18 feet in length, but we don't know the height of the light pole. And so, you can measure it directly, but this lesson is dealing with indirect measurement. So knowing information about how these two triangles are related, hopefully you see the triangle here that is formed from the shadow, that will allow us to solve these problems. So there's a couple things that have to work before you can do this, and that has to be that the two angles have to be congruent in each of the triangles, and if that is true, then the triangles are similar, and then you can use the comparison of one triangle to the other. And just as always, we should assume that all three angles in a triangle will total 180 degrees. So if this first statement is important, and it is, we are going to need to look at these a little bit more carefully here. So you'll see in the instructions it says write and solve a proportion, and we'll get there in just a second. But if you look at this example here, a little too fast, we have a person standing here, and we don't know how tall they are. They again are casting a shadow that is 7 feet in length, and then we also have a mailbox that stands 3 feet in height and casts a 4-foot shadow. And if you look at the way the problem is set up, it shows us here that this is a 90-degree angle and a 90-degree angle. So we know that those two sides are congruent. Remember, congruent means equal. And then we have 2 lines here and 2 lines here. Now we don't know the exact measurement of the angles, but we know that those are the same. Since they have the same 2 arcs on there, we know that those are the same. And in fact, this angle up here is the same as this angle as well. So through the definition of similar triangles, these are similar because they have 2 congruent angles, and so that's where we can use a proportion. So I'm going to just show you all the steps here. You'll notice that I have h on top because that's what I'm going to solve for, the height of the person, and then across from that is the other number that represents the height of something. Well, that would be the mailbox. The mailbox is standing 3 feet in height. The 2 bottom numbers are both the length of shadows, and the 7 must be underneath the h because it is in reference to the person here. So they have to be together. And then the 4 is connected to the mailbox. We would get the wrong answer if we changed the placement of the 4 and the 7. If we swapped places and put the 4 underneath the h and the 7 underneath the 3, because then we're not showing things that go together. Remember, both of these things represent the person. Both of these things here go, 3/4 goes with the mailbox. And so at this point, it's back to what we did in, chapter 1 with solving proportions. We're going to cross multiply. So we're going to use butterfly multiply. So we will multiply 7 times 3, and we will multiply h times 4. And at this point, it's like the last chapter. It's going to be a one-step equation. So if I have 4h equals 21, I would divide both sides by 4. 21 divided by 4 gives me 5.25. We could also write our answer as 5 1/4 feet. So we know now the height of the person standing 5 1/4 feet, but we didn't have to use a tape measure. We used all the other information that is provided in the problem in order to determine this height. So the steps of the problem, once you can match up the sides, is really just using proportions for each example. So let's look at another one. This time it's a little bit different. We're still kind of dealing with that same height and shadow type of problem. But you'll notice this time that the triangles are inside of each other. Makes it a little bit harder to figure out here, but if you look closely, so we know that this is a 90-degree angle here, but there would also be a 90-degree angle here. These are both right triangles. And then we have the one arc here, and then there's one arc here. So this makes it much easier when the triangles are facing the same direction like that. It can be a little bit tricky when they're not. You're going to see some other examples where it's a little bit harder to tell, but they're lined up pretty well. And so we can see in this problem that we are solving for the height of the flagpole. It's h. We do know that it's casting this shadow that is 31.5 feet long. We also know the height of the person this time at 6.5 feet, and they are casting a 9-foot shadow. So if you kind of pay attention to what's happening in these problems, we are given 1, 2, 3 pieces of information, and then we are solving for the fourth, and that's what allows us to use a proportion in solving these problems. So I know a lot of work that I just put up on the screen here, but I would follow it step by step. We'll start up here at the top. So I put h on top, and then I put the 31.5 on the bottom, because this is the height of the flagpole, and this is the shadow that it's casting. I can't put 31.5 over on the other side of the problem. It has to be with what it is connected with. Remember, flagpole would be connected with the shadow of the flagpole. So then over on the other side, I put the 6.5 foot in the top because that is the height of the person, similar to h is the height of the flagpole. Again, placing some of these things in the wrong spot would give me the wrong answer. It would be possible to put the 31.5 on top and h in the bottom if we put the 9 also on top and the 6.5 on the bottom. So there is some degree of flexibility, but I can't put, other than this option and that option, I can't do anything else. So then, this one's a little bit trickier. We cross multiply again. Notice we're going to have to multiply 31.5 times 6.5, and then 9 times h. So I went ahead and showed you 9h, and then here's my step-by-steps of multiplying these fractions. Since I went ahead and made them into improper, 63 over 2 and 13 over 2, and then I multiplied and I got even kind of a more yucky fraction, 819 over 4, and then I know it's a one-step problem. I can't forget about this 9 over here, so I'm going to divide both sides by 9. 819 over 4 divided by 9, so we're going to use keep, change, flip, and so I will leave that first fraction, change division to multiplication, and change 9 over 1 into 1 over 9, and I went ahead and just multiplied straight across. With numbers this big, it's really tricky to try to figure out what they have in common. And so now at this point, I need to really reduce this to make it look like something that makes sense. You know, having an answer of 819 over 36, we've said before we like improper fractions, but that's just a little bit messy when we're dealing with the height of a flagpole, and I don't really know what the whole number is. So I went ahead and divided them, and I got 22.75. So we know that the height of the flagpole is 22 3/4 feet, or 0.75. Either answer is correct. So hopefully you can kind of see how this could be a realistic thing. Measuring a flagpole that stands over 20 feet tall wouldn't be a very easy thing to do. But if we knew the shadow length and we could find other corresponding shadows and heights of things, as long as we could determine that we had the correct angles, we could determine the height of that flagpole. So this one is a little bit trickier yet because you can hopefully kind of see it here. There's a triangle here on this left side and then a triangle here on the right side. And if I start looking at those arcs at the way things match up, really to get these to match up correctly, it would almost be helpful to redraw this triangle flipped over. So let me just do that real quick because I think it'll be easier for you to see. So if I could cut this like right here and fold this over like a piece of paper, what would end up happening is I would have a triangle kind of about like this. Mine's not nearly as neat, I know, but it would fold. Hopefully you can kind of see how that would be. And this 21 would be here, and this 10 would be here. And that hopefully makes it a little bit easier to see what goes with what. Maybe you could already see that D was going to go across in the proportion from 10, but I think it's a little bit harder to tell in that placement of the problem. So when we go to set that up, it's going to look something like this. So again, remember what we had. We had 45, and we said this 21 right here went with that. So they're going to go across from each other. So we have one distance here and one distance here. And then we have D distance between the roller coaster and the water ride, which is D. Again, it's underneath 45 because it's connected in the same triangle. And then the 10 is in this other triangle, so it's going to go down here. We cross multiply again, 21 times D and 45 times 10, so then we would have 21D equals 450. Divide both sides by 450 and we get, divide 450 by 21 and we get 21.42, and I just rounded that to the nearest tenth because that's what the instructions say. And so then we find our answer of 21.4 meters, and that is how far the water ride is from the roller coaster. But yet, that measurement here was never found directly. We found it indirectly through these other numbers. And one last example here is draw a diagram for the situation, then write a solve a proportion. At the same time, a 2-meter street sign casts a 3-meter shadow. A nearby telephone pole casts a 12.3 meter shadow. How tall is the telephone pole? So, so I did not draw a diagram of this. I can go ahead and do that for you. I only have a couple minutes left in the video. So it says a 2-meter street sign. So if that is, let's say this is 2 meters. Casts a 3-meter shadow. I can make that into a triangle. A nearby telephone pole casts a 12.3 meter shadow. So 12.3 would be in the bottom. And we are trying to figure out how tall that is. So that is X or H or whatever variable we want to make for that. Now again, I made these both right triangles. They're not very pretty, I know, but then again, we should be able to see that 2 and X would go above each other here, and the 3, you know what, this is actually at the same time a 2-meter street sign casts a 3-meter shadow. So looking at this problem a little bit more carefully, the answer that's shown here is correct, but my problem is set up a little bit incorrectly, and you gotta be, this is what I was kind of warning you about doing this. All that's different is going to give you the exact same answer, but this should not be an X. It should be the 3. And the reason is, remember, this is the shadow of the street sign. No, I'm sorry, this is the shadow of the street sign. It's 3 meters. It's casting a shadow of 3 meters, and it's 2 meters in height. So these go together, but then X is the flagpole, its height, which also goes with the shadow of the flagpole. So you might think it doesn't really make any difference, but errors like that where you put things in the wrong spot can sometimes give you the wrong answer, especially if I were to move the 3 over here. So the answer is correct. We still will get 3 times X and 2 times 12.3, which will be 24.6. Divide both sides by 3, we end up with 8.2. But just a little caution to you there that I made that mistake in how I set it up. That's how you do problems that involve triangles and indirect measurement. Only 5 problems for homework, but they are a little time consuming, a little tricky to set up, but we are going to use proportions to do that.